Hello guys, welcome to part 2 of the Gaussian process video. This is Sarnath, and if you haven't watched the part 1, you could watch now. The YouTube link is there. So this demo is going to be on Jupyter Notebook. Let's do the initial inputs. Check. Here in this one, I have loaded the NB Black extension. It's an automatic code formatter for Jupyter Notebook. Let's say that we have got a clumsy cell like this, right? Somebody has written a clumsy code like this. You execute it automatically, it formats. Isn't that cool? I have also used this Jupyter Contour NB extensions, which helps me with this collapsible headings and all that. Apart from the installation, it also comes with the post-install instructions. So please ensure that you Google, you find this instructions and install it properly. Right? And this notebook is in GitHub. It's in my github.com/sarnathk/gb tutorial. You could clone it from here along with all the supporting materials, right? And if you're looking for an authoritative reference book for Gaussian process, you should look at the book from Rasmussen and Williams. Rasmussen is the person who developed Gaussian processes. So I have given the link to the book as well in this notebook. So let's get started. Let's start with some basics, right? Univariate probability distribution. You should all know about the rolling of dice, which is a random variable, and it can take discrete values like 1 to 6, and it's uniform 1/6 for a fair dice. Then we also know about the binomial distribution, which talks about, let's say, if I roll this dice 10 times, what's the probability that I get 7 times? What's the probability that I get an even number 7 times, right? What's the probability that I get an even number 3 times? So like that until 10 times, all the way to until 10 times, that forms a distribution that is called the binomial distribution. And we also have geometric distribution, like number of times you failed before your first success. For example, number of interviews you flunked before you got selected by somebody, or the number of times you failed in the parking test in Dubai, RTA test, number of times you failed until you got it right. So all these form geometric distribution, and similarly there are many distributions. The point is that the value taken by that random variable is discrete. Number of times you fail is a discrete 1, 2, 3. You cannot fail 2.5 times or 2.34 times or something like that. So these are discrete distributions. So the continuous analog, we can take an example of the Gaussian distribution. In this case, you can see a big formula out here. X is the random variable. It takes a continuous value. Mu is the mean, sigma is the standard deviation, and the term x minus mu by sigma gives you how many deviations x is away from the mean. The entire thing is squared, so even if it is positive or negative, it has no impact. So it doesn't matter whether you are the left side of the mean or within the right side of the mean, this term produces the same value. And then it's exponentiated, which means that if it is a bigger value, your density drops. So the density is highest at mu, where x minus mu by sigma, the entire term vanishes to 0, right? So this is an example of a continuous distribution. So let's move on to multivariate distribution. So far, we just saw only one variable, right? The number that came out from the dice is just one number, right? The number, in the Gaussian distribution case, the x is just a single number, right? It could be just the height of a person in a population or whatever, right? So in case of a multivariate distribution, you will have more than one variable. So in this case, we are talking about two variables, rainy and weekdays. Now you might ask, rainy, I can understand, it may or may not rain, it's a random variable, but weekday is something that is known, right? Like we know that Tuesday comes after Monday, Wednesday comes after Tuesday, and so on. Why is it a random variable here? Right? So in this case, you just imagine that you're randomly sampling a day in the last 100 years for a particular place. For example, we are talking about Bangalore. So in the last 100 years, we just pick a random date in Bangalore and examine whether it rained on that day or not, and what weekday it was. In that case, you can think that the weekday is a random variable, right? So in such a case, rainy and random variable together form a joint distribution, and you can see that the probability that it is rainy and it is Monday is 0.02. The probability that it's rainy and it is Tuesday is 0.03, and so on. So you can read this table easily, not a big deal. Now the last column and the last row are somewhat different. They total, if you look at the last column here, the total represents whether it is rainy or not. What's the probability that it's rainy completely, right? The last column represents what's the probability that it's rainy, and the last row represents what's the probability that it is a weekday. If you look at it, in this case, both the column and the row, we are only talking about one variable, which means that we marginalized out the other variable. In this case, in this column, we take probability of rain is yes, and then, sorry, we take the probability of rain as yes, and then we add all the joint distribution variables associated with yes, but with other variables, right? So we add up all those numbers and you get this 0.42. So 0.02 plus 0.03 all the way until 0.07 is 0.42. Similarly, you can say that we can add these two and get this number. So we are basically marginalizing out a variable. So you take a two-dimensional distribution and then we just marginalize on one variable and you get a one-dimensional distribution, right? That is what is called marginalization. And what is conditioning? Suppose that I know that today is Tuesday, and what's the probability that it's going to rain? Now we know that we have to focus on this column alone. We are not interested in this entire table. We are focusing on this column. If it's going to be Tuesday, we know that 0.03 for a Tuesday, and we already know it's Tuesday. 0.20 is already covered. So 0.03 by 0.20 is the actual probability that it could rain, given the fact that today is Tuesday. This is same as the base formula. It says P of A comma B is nothing but P of A and B, which is nothing but the joint distribution of A and B divided by P of B, right? In this case, joint distribution is 0.03, P of B is 0.20, and then we get 0.03 by 0.20, and that is how it works. Right now, if you go to multivariate continuous distributions, in continuous distributions, there are multiple dimensions, right? And then you have this, we are looking at multivariate normal distribution. This formula might seem threatening a bit, but it's easy. Sigma is the covariance matrix. We are taking an inverse of that. Let's assume for a moment that it is identity matrix. If it's an identity matrix, we can remove it from this equation, and what is left is x minus mu transpose into x minus mu, which is nothing but the dot product of x minus mu with itself. And what is that? It's just nothing but sum of squares of the distances of each dimension from the mean, right? And that is what it will yield. So, and this is, prefixed with a minus half, so which means that as this number increases, as you move away from the mean, this number becomes a huge negative number, exponentiated, and so the density drops, right? And you can see that if you are in x, since x minus mu is a multi-dimensional variable, if you are off the mean in any of the dimensions, it will produce a big number, right? It doesn't matter which dimension you are moving off the mean. Whichever dimension you move off the mean, your density will fall down, and density will fall down equally on all the directions the same way, right? So that is the way to look at this formula. And Gaussians have two important properties. To understand Gaussian processes, we have already seen that Gaussian processes are closed under conditioning and marginalization. I already explained what is conditioning and marginalization with respect to discrete. I'll explain it using a nice figure. This I got from Wikipedia. So if this is a two-dimensional Gaussian distribution like x and y. Now, what is meant by conditioning? Conditioning means I have to fix the value of one variable. If I fix the value of x to be 80, right? At 80, you see that line that is going here, right? The one that goes at a small ebb around y is 40 or 50 and then goes down, right? That is the conditional distribution of y given x equal to 80, right? So each one of those wires that are going like this wireframe, so each one of them represents the conditional distribution of y for different values of x. You can see the wires on the other side that represents probability distribution of x when y is nailed, right? In a multivariate distribution, you can condition on any one of the dimension, doesn't really matter, right? So if you nail it on, if you nail y to be 50, then you get this wire that comes from 50 that forms the conditional distribution of x, how x can be distributed. And we know that yeah, so in this case, whichever way you condition, the resulting distribution is Gaussian. That is the property of Gaussian stuff. And for marginalization, let's say that if you want to marginalize on x and we want to marginalize out y, so which means that for each value of x, you take this distribution out there. You take this density curve, you take the density curve and add it up. If you add it up, you will get a value, right? And that will be the value of x density. So that's what is called marginalization. It's just summing up all the values of x associated with y and then eliminating y totally, right? Now you might ask, since you said that this is a conditional distribution, right? It's a conditional. If I add all of them, I should get one. That is not the case. I'll explain why. Because the probability distribution is multivariate, which means that if you have to add all those lines to get that one, a single line will not produce one here, right? A single line will produce only a minuscule number. So when if you marginalize, you're not going to get one for every x, right? So that is clear. And for conditioning, that value, right, that value must be divided by the value of the conditioning. You need to add up all that and divide it, then only it will become one, right? So you need to divide it by the marginalized value of x, so that it will give you the actual you basically need to normalize this density so that it can become a probability distribution. But that is just a nuance, you don't have to worry about that. But I hope it's clear what marginalization and conditioning is. Right. So the point is that if you have a multidimensional probability distribution, which is represented by x, y, mu x, mu y, and this is a covariance matrix. Here A represents covariance of x, C represents covariance of x with y, C transposes y with x, and B represents y with y. Right. So if we have build this covariance matrix and represent the distribution this way, if we marginalize out y and then x alone remains, then x would be a normal distribution with mu x and a, right? And it has no dependency on y at all, right? Because we have integrated out y completely, right? So this is a Gaussian. So that is the good thing about it. And if you're looking at conditioning, right? If I say, okay, if I take a Gaussian distribution like this, and then I condition x given y, then the conditional distribution is also a normal distribution. You can see this n here, normal distribution, and the mean and covariance can be analytically worked out, right? So if you're more interested to figure out why this is so, where does it coming from, I recommend that there is this beautiful stuff from Fabian Dablander, where he derives both these formulas properly. For multivariate distribution, he starts with bivariate, and then he extends it to multivariate. Well, a very detailed information is given. If you are interested in that, please do that. And there is also a YouTube video from Mathematical Monk. I like that. I like that video as well. It's pretty good. It's not going, but it's out there. So if you look at this is the youtube.com. So this is the URL. You should be able to get that, right? You can get it from the notebook. So that is also very interesting. Right now, these two are out of our way. Let's actually go and let's plot some distributions, right? For example, if it is a two-dimensional distribution, I'm using NP random multivariate normal function, and here I'm giving the mean as 0, 0, and this is the covariance matrix. I'm giving it as an identity matrix, which means that these two dimensions are free to change. You can say that most of the numbers that you get a 2D number, you get a two-dimensional number, two numbers, and this will be close to 0 only. So if I change this to 30 and 30, 30 and 40, you will see that the numbers that are returned are close to 30 and 40, because that is the mean of the random distribution. Right now, I can do the same thing for a three-dimensional as well. Let's say that I take a three-dimensional Gaussian distribution, and then I specify a covariance matrix, which is nothing but an identity matrix, which means that all three dimensions are free to change as per their wish, right? This is what you get. You can probably change this to 10, and then you'll see that the second number in the vector that you're getting is close to 10, right? This is what a multivariate normal distribution is. Now let's plot some of these, right? So take x, y, go scatter. So this is nothing but I just took a normal distribution with the identity matrix as the covariance matrix. I sample this two-dimensional random distribution, and then I plot these random samples, right? So you see that it's centered around 0, 0, and in radially in all directions it is uniform. There is no specific direction to this distribution. You see that this distribution is completely random, and it is like this because the covariance matrix is an identity matrix, which means that there's no relationship between x and y. They're all centered, both of them are centered at 0 and then reduce uniformly on both sides very equally. So that's why you get the scatter like this. Let's say that instead we look at some correlated samples. How does a correlated 2D sample look like? This is how a correlated sample looks like. So in this case, when x is positive, like y is also positive. When x is negative, most likely y is negative, right? So there is some kind of a dependence between x and y. And if you position 0 comma 0 and you go radially outward, you know that in this direction you have to go really really long so that the distribution fades, right? Whereas in other directions, the distribution fades pretty quickly, right? That is another indication that there is a correlation going on. Now let's find out in this correlated distribution, if I nail the value of x, what is the distribution of y? Right? If I nail the value positive in the if they nail the x to be a positive value, then y will have a positive distribution. If I nail the value of x as negative, y will have a negative distribution, right? Or the mean of that y distribution will be negative, right? So let's do the same. See, when I'm conditioning at x equal to 3, this distribution, what I'm doing is that I'm taking a random sample. Only if x is close to 3, I retain that random sample. Otherwise, I discard the random sample. So I'm repeatedly random sampling. Whenever that is 3, I just hold on to it. Now you see that the mean is somewhere around 5, not even 5. This is 5, this is somewhere around 4, right? Maybe somewhere around 4, 3 or 4, right? If I do the same thing at minus 3, you can see that when x is minus 3, right, the mean is at minus 3 or something like that, right? So this is the distribution of y depends on the value of x, right? So when you have a multidimensional probability distribution, the value of one dimension can dictate the value that can be taken by other dimensions, right? And this is a very fundamental concept. We have seen this before in part 1, that this is a very fundamental concept we need to understand. The value of one dimension can affect the value in another dimension. What's the probability distribution of the other dimension? Right now, we can take functions as random samples. How? If you take, if you want to plot 50 points of a function, just go and take a 50-dimensional distribution and take a random sample, you get a vector, right? Because we saw that if I take a two-dimensional, if I random sample a two-dimensional distribution, I get 2 points. If I take, if I random sample a three-dimensional distributions, you get 3 points. Now I think I can just random sample a 50-dimensional function and then plot it, right? I'm just taking only one random sample here. I'm just taking only one random sample. Plot random function. Ooh, this is what. So let me plot it again and again. It keeps changing, right? This can be seen as a function, right? How is this different from the scatter plot I did before? In the scatter plot, I had a probability distribution that is two-dimensional, right? And then I took a lot of random samples from that. So I get a lot of x comma y points, and then I'm plotting it on the chart. In this case, I do only one random sample of a 50-dimensional distribution. So I get 50 numbers. I just plot it as if it is a function, right? Because ideally I should plot it as a point on a 50-dimensional chart, but that is, we are talking about a 2D screen, right? So I cannot plot more than 2 dimensional, at the max 3 dimensions, right? So instead of that, instead of looking at the point as a vector, we are just looking at the point as a n-dimensional vector. We are looking at the n-dimensional vector as a function, right? And then we are plotting it. So it's kind of funny, right? Which is interesting. Now I can actually study what's the effect of covariance on these functions, right? Now, for example, in this case, what is the covariance matrix I have used, right? I'm just taking a covariance matrix as A transpose into A. And what is A? A is just a random normal. I just create a random normal and then I take a transpose of that and multiply with itself. Right? That's what I'm doing. Right? So it's just a random matrix. The only reason why I'm doing A transpose into A is because A transpose into A has to be a positive semi-definite matrix. If you want to know what is a positive semi-definite matrix, you go here. If you go to this function, see, in this case, sigma inverse, right? If this term x minus mu transpose into sigma inverse into x minus mu, if this term returns a negative number, the entire fundamentals of Gaussian distribution will fall down, because the exponents, because when this number becomes bigger, I should actually have a negative sign, and then you should go down. When you're, as you're moving away from the mean, the density should fall down, right? This term should always be positive, right? And that is guaranteed if this sigma inverse is a positive semi-definite matrix. Okay, this it will never be negative. This equation, if you take a vector, you multiply, if we take a vector's transpose, in this case x minus mu transpose, if you multiply that with a positive semi-definite matrix and then you multiply that with the vector again, it will never give you a negative value. That is what is the definition of positive semi-definite matrix, right? And with positive semi-definite matrix, one way of identifying a positive semi-definite matrix is to look at their eigenvectors, right? Eigenvector, it has to be symmetric first of all. See, this is what I just check whether it is symmetric first. It is symmetric. A symmetric matrix with real and positive eigenvalues will be a positive semi-definite matrix, right? Don't ask me how. And I know that A transpose into A will give me a positive semi-definite matrix. Now I have also verified it, right? Although I don't know that A transpose into A, I'm just following some random some previous knowledge, but I can actually empirically verify that I am getting a symmetric matrix. True, a symmetric matrix with eigenvalues all positive, and there is no all real numbers. There is no complex number in this eigenvalue, right? Once you verify that this is good, this covariance matrix is good, and that is what we are using. And as such, it's a random covariance matrix. What is a random covariance matrix? It means that the value taken by the function in this dimension has no bearing. It does not dictate the value taken by other dimensions, right? So each dimension is free to vary, which means that you are getting a spiky function. But if I introduce a covariance matrix that says that the value taken in this dimension affects the neighboring dimensions, then the neighboring dimensions will be close to this. If the neighboring dimensions are close to the value taken by this point, which means that you will get a smooth function, right? So let's try it out. So in this case, what I'm doing is I'm constructing a covariance matrix for I in range and j in range. This is nothing but this is how the symmetric matrix is created. I just use a function that basically takes I minus j, take the absolute of it, and then I square it. I use the negative square, just like how I do that here, and then divide it by 75, some number. I'll talk about 75 later, right? So basically what it means is that if I and j in this 50 dimensional vector, if we take a 50 dimensional vector, neighboring dimensions will have a higher value here, and as the dimensions are far away from each other, they will have a lesser and lesser value. As simple as that, right? Now if I do this smooth function, this is cool, is it not? This is nice. This is really good, right? Now, what's the use of 75 here? So in 75 here basically means that if this I minus j is holding a big value, let's say that if I make 75 7,500, what happens is that even if you're 50 dimensions away, 50 squared is what? 2,500, it will still be a small value only. If you divide by 7,500, so which means that it will ensure that there is the variance in this dimension, the value taken by this dimension is determined by this dimension, which means that they cannot change a lot, right? It's just they cannot change a lot. The number of curves would reduce, right? So that is what it means. So this parameter is called as a scale parameter in Gaussian process. It can affect which dimensions affect what, right? And if I reduce this, let's say I reduce it to 7, what happens? right? It degenerates. You see that? It degenerates to the spiky functions we have seen earlier, right? So we use 75 here. And be happy to have 75. What happened to you? There was a problem. Okay, I did something. I failed to close the bracket. Okay, now we got back to our smooth functions. Nice, right? So again, to refresh your memory, it is just a 50-dimensional Gaussian. I define a 50-dimensional Gaussian distribution. I create a covariance matrix such that neighboring dimensions are correlated more, right? And then I just take a random sample from the 50-dimensional probability distribution. I get a 50-dimensional vector. I just plot this 50-dimensional vector as if there are 50 points close by, right? And then I see it as a function, right? Because in the function view that I discussed in part one, a function is nothing but the domain values become the dimension, right? And the function becomes a vector. Value of the function becomes a vector. So each one of the dimension can be seen as a domain value. In this case, the domain value is 0 to 50. That's all, right? Now we can condition. Now let's condition this. We know that if I specify the value of any one of the dimension, let's say that if I specify the value of the function at 15, it should have a bearing on the function. So I will get a family of functions which are close to 15, correct? That's nothing but a conditional distribution, right? So I can take a 50-dimensional function and then I specify the values of certain dimensions. Then I can take a conditional distribution of the rest of the dimensions and then figure out and then plot it and then see how it looks, right? I can condition them. This is basically a random sample and we have got 50 dimensions. We can condition certain things, right? So what I'm going to do, I have a tolerance, I have written this function which basically does multiple random samples. It does multiple random samples until it find something that matches the condition that I specify. What's the condition that I specify? Here, if you look at it, the value of the function 0 has to be 0.5. The value of function at 5 has to be 1. 25 is minus 1. 40 is 1.5. If I say that, now I go ahead and random sample. I throw away the samples which are not matching which are not close to this 1.5. I cannot get an exact match. Otherwise, I will have to keep sampling throughout the day, right? So I put a tolerance. And I'll give some allowance, right? And then we do this. Cool. See, now if I repeat this, you can see that the functions are somewhat limited. They have to, these points constrain how this function can behave, right? Interesting, right? So there is a constraint. So this is what conditional distribution does, right? The conditional distribution is basically constraining the values of the function taken in other dimensions, right? Very interesting. Now, if we just go, we know that we have seen the formula for conditional distribution, right? We already saw this there. I can show you here as well. Here also there is a conditional distribution formula, right? So instead of randomly sampling 100 number of times or 500 number of times and then discarding all the random samples and holding on to only points that matches the condition, right? Instead of doing that, we can actually use the theoretical formula to do this. You don't have to do anything like, see this? It was very instant. We are just applying a formula. That's all. You can see that I have specified so many points, the function is not able to vary so much. Right? Now I can, instead of doing like this, I can specify 20 outputs. Right? Now you can see that I've taken 20 different samples, random samples, and you see that the place where there is a lot of variance, right? It's here, here, here. When you're moving away from the points, when there are a lot of points nearby, there are 4 points nearby, and you see the function is not able to change as much as it is doing here, right? So if I specify a point somewhere between 60 and 80, let's specify 70. 70 is minus 6, right? Minus 10, we'll put. We do that. See, suddenly that stopped, the variance stopped here. Right? Similarly, between 40 and 60, let's put one number. 40 and 60, we just put 50, I'll just put 10. 40 is minus 10, 50 is 10. Horrible it is. Let's see how what it does. Yeah, no problem. We got it. No problem. See, we don't have to repeatedly sample things, right? Now we have got variance here and here. If I specify points here, then that variance will also die down. Right? Now you see, if this is my training set, if these points are my training set, and if I seek an inference at this point, I will get a probability distribution, right? Because these lines are coming from a probability distribution on these. So I will get a probability distribution with more variance here, with less variance here, right? And now you see why Gaussian process is a good interpolation technique. If you move away, see how much variance it crosses. This place is messed up because it's away from all the points, right? So in Gaussian process, always remember that if the output variance is too much, then you're very much away from your training data set. And that is one of the advantages of Gaussian process as well, right? So let's move on. Let's do a Gaussian process regression through a hand-coded example. Okay, this is just a random data. I hope I could generate a good data, but I just randomly created this data. It's my own creation. It can be bullshit, but at least for concept elucidation, I hope it helps. See here, we have to figure out the time to complete the physical task given the height, weight, age, BP, systolic, diastolic, and fasting sugar level of the concerned person. So basically, we are taking a stab at the health of the person and then trying to see if it is correlated with the time to complete a physical task, right? So this is what we want to do. And then we want to answer this question at this 5.12, 52, 23, like what time these people will take to complete the physical task. Can I answer it from these points, right? That is, this is what most of the regression analysis would focus on, right? So let's see how it works in Gaussian processes. Right now, since I want prediction of this, I can take this, each one of this is a domain point, right? Each one of this is a domain point, and this is a range, right? And then we have the domain point for the point where we are seeking prediction. We just don't know what's the range values here, right? Now we can combine all these domain points together into a single domain point array, and then we can create a covariance matrix on top of that. What is a covariance matrix? Between any I and any j, you have to create a covariance, right? So for example, between 1 and 3, you take this vector 6.23, 634, 128, and 342, and 4.45, 50, all the way until 82, and then you take these two vectors and create a covariance value for it, and this can be a covariance function assets. This is just a function, and that is one of the beauty of Gaussian process, because your domain can be messy. It can be a vector or it can be an image also. It can be anything. Your domain can be anything, as long as you can compare two elements and create a covariance relationship between those two. We're all set. We can use Gaussian process, right? So Gaussian process has another advantage like this as well, right? So now if we can create this covariance matrix, right, this one has 3, 6, 9, 12 points and 2 points, right? So totally you have 14 points. Let's say we create a 14 cross 14 covariance matrix. Then this function, whatever function that is governing this, can be thought of as a random sample from that 14 dimensional distribution, right? If you sample a 14-dimensional distribution, you get a 14-dimensional vector, right? So that can be seen as a random draw. So we are creating, so just by creating this covariance matrix, we have created a probability distribution and a family of functions, which are very similar to the function in question, right? Now this particular random sample, the values are known here, which means that if I specify the values of this dimension, this remaining two must be a conditional distribution, right? And if you take the conditional distribution formula, you will directly figure out the values for these two as a probability distribution. What you get is a joint probability distribution, but you can just ignore because we are not interested in the covariance between this point and that point. We are only interested in the variance in this point. So you just look at the diagonal of that conditional distribution, and then you can get your variances from there, right? So without much ado, so I have just combined this into one single point. There is something called known dimensions. This has 12 points. This has 2 points. and there is known values, right? Whatever it is, I have just put it here, right? uh, I hope there are no changes here, right? It matches, right? It matches. Okay, good. So known dimension shape is 12 cross 6. This is 2 cross 6. Now I just take a covariance matrix from the known and the unknown. So that is, this gives me the covariance space, right? If you look at this covariance space, oh, it's huge, huge numbers, right? Because in this case, I'm just using a linear covariance. There's no function. It's just a normal covariance that we use in statistics, right? I've used the same definition. Okay, this is a covariance matrix, huge, huge numbers. Now I figure out A, B, and C. What are A, B, and C? It comes from this formula, right? So it comes from this formula, but in this case, they have given X, given Y, right? But what we are seeking is Y, which is at the bottommost part of a matrix, P of Y given X. So there is some, so accordingly, it has to change. But the ABC comes from this formula. I want to apply this conditional distribution formula. So for that, I need C, B, A, and all that, right? So I take this unknown dimension with known dimension as A, B, and C. Then I find out the mean using the formula for conditional distribution. And your covariance is a joint distribution of the 2 cross 2, but we are only interested in the diagonal, right? And you can see obviously that this is bullshit, right? Because we don't see this kind of variance in the data. Because the time taken to complete a task was never had this kind of variance. So obviously this is stupid, right? And what is the stupidity? Because we did not scale the data. Each one of these dimensions, see, for example, sugar level is 300, it's in hundreds, right? This one is in tens, 0 to 10, within 0 to 10. Weight is between 10 to 100, right? So each one of them is in a different dimension. If we just calculate distance, if the concept of distance between vectors, where each vector is in a different unit, then the dominant unit will start dominating the distance. For example, 342 versus 100 is like 200 squared. If you are simply taking the distance between this is 200 squared, and this starts dominating the distance between the two variables, the Euclidean distance. If at all you are using Euclidean distance in your formula, this will start dominating, right? So because of that, what we need to do is we need to do a standardization of these variables. What is standardization? It's called standard scaling, which where we calculate x minus mu by sigma for each column, right? So x minus mu by sigma does not have any units associated with it, right? X minus mu by sigma basically tells how many standard deviations you are away from the mean. That's all. This is just the number of standard deviations you are away. So it has no units. So this is how we normalize, right? And then if you look at the NP max of this, let's see, 2.7, it's a reasonable numbers. And then for the covariance matrix, again, I'm going through and doing the for loop for each one of those points. I just calculate the covariance using the simple distance. I calculate the distance between I and j, and then I take an exponential negative of that distance and divide it by scale, 2 scale squared, right? Scale, we have already seen what's the purpose of the scale. Right here, I'm passing a scale of 2.5. I'll show you for different values of scale how the output is affected. This is your covariance space. Now it looks like a reasonable set of numbers, right? And then I take RBFE, RBFP, RBFC. Then I take this covariance. Now you see that the prediction I got is 2.18 with a standard deviation of 0.04, right? After this is the variance, sorry, this is the variance because this returns the variance, right? For standard deviation, I need to take a square root of this, right? So similarly, I got a prediction with 3.54 mean with the variance of 0.15, right? So I need to take a square root of this to get the standard deviation, right? So right now I have provided the output with variance, but for standard deviation you need to take a square root, right? Perfect. Now when we develop models like this, we need to understand whether this guy point this is this sensible, right? We need to know why the model chose that output. It's very important for all data scientists to go and figure out why the model is saying this output, right? In our case, we know that the covariance space dictates the similarity between data points, right? We have seen that, right? because the RBF formula that we use basically looks at the distance between them, and then we take and then we square that distance, or then exponentiate and all that, right? So if the distance is less, then you will have a better value for the covariance, right? So that's what we are trying to do. So in this case, we are looking at the covariance matrix, which is 14 cross 14, right? We want to look at that 13th and 14th entry, right? 13, comma, this is the last entry, 12. So the number is, the indexing is 0 based. So this is the covariance entry of this point. Which point? The point at which we are seeking prediction, right? 5.12, 52, 23, 134, 84, 183. For that point, right? This is your covariance entry. And if you look at it, the second entry has second row. It's highly correlated with 0.86 with the second row, and then a third row is also good. But what are the top two rows? If you look at it, second, third, four, five, six, seven, eight, right? Second, 8, 9, 10, 11. Second, 8th, and 11th point. So what this means is that this particular guy, this particular point at which we are seeking prediction is very close to 2, 8, and 11. What is 2? Look at this: 5.2, 5.12, 56 versus 52, 37 versus 23, 145 versus 134, 80 versus 84, 242 versus 183. And this guy did the job in 1.34. Okay, now let's go to 2, 8. 1, 2, 3, 4, 5, 6, 7, 8. 8 is also 5.2. 56 versus 52, 25 versus 23, 115 versus 134, 74 versus 84, 142 versus 183. This is also pretty close. And in this case, they are doing 3.04, like 1.34, no, 3.04. What about the 11th one? 9, 10, and 11. It is like 4.67 versus 5.12, slightly off. 60 versus 52, okay. 12 versus 23, slightly off. 135 versus 134, very close. 95 versus 84, 104 versus 183. This is somewhat close only, but 1.94 is what they have given, right? So there are three dimensions which are influencing. 1.34, one of them had 1.34, another had 3.04, this one has 1.94, and finally it has settled down in 2.18, right? It's neither 1.34 nor it's 3.7. It's kind of settled in 2.18, and this, it has got a covariance, standard deviation of 0.04, which is nothing but variance of 0.04, which means the standard deviation is close to 0.2, right? So 0.2 is like 2.18 to zero point 0.2, and since it's a 6 sigma, you can use minus 0.6 to plus 0.6. So somewhere between 1.4 to 3, right? Exactly, it's coming like that, right? Maybe it's not because of that, but at least we can verify it that way. So that is what it is saying, right? Similarly, now when you build covariance matrices, it is important that you go and take the point at which you are seeking prediction and then see what they are correlated with in the training data, and are they really similar in the training data, right? Or will you consider them as similar according to your application criteria, right? So that is what you should look at, and that is why the concept of covariance kernels is very important, right? The choice of the covariance affects which points are similar to which other points, right? So if you choose a bad covariance for your application, you will get bad predictions. So the choice of covariance matrix is extremely important. For that, you will have to do some cross validation and do some hyperparameter tuning, which is pretty good because you have a choice of covariance function. Every covariance function has a lot of every covariance function will have a lot of what do you call uh, every covariance function will have a lot of hyperparameters too. For example, in this case, in this RBF, we had something called scale. What happens if we increase the scale? If I increase the scale, if I go here, you see every point is close to this 0.85, 0.96, 0.91. This is not something desirable, right? So maybe if I use 1.225, what happens? Right? So 2 is better, somewhat better, not that better, just figure it. So probably 2.5 sounded good for me, right? So in this case, so similarly, you will have to experiment with different values of scales, look at the prediction, do the cross validation, and figure out what actually worked for you. So it's totally So there's a lot of things to tune here. And if you're looking at kernels, there's something called a kernel cookbook, advice on covariance function. It's a very nicely written documentation. It is also referenced in scikit. In scikit Gaussian process, that is a reference to this kernel cookbook. You can go to this kernel cookbook and look at various different kernels, on what conditions you need to use those kernels and all that. So that brings us to the end of our session here. I hope this was useful. If you need any question, if you have any questions, if you need any clarity, please write it as a comment in my YouTube video. I'll definitely address them. Okay, all the best.